I'm very happy to be here and part of this really exciting event. For several reasons, I think. One of them is that actually there was a subtitle to my presentation as well, which actually was saying about a few words about the threats of, so to say, excessive data centrism. And that actually will be the revolving theme of my specific talk. And when preparing that talk, I was afraid that that would be a bit like throwing a spanner in the works, right? But I can see that actually this theme somehow resonates and reverberates from the very beginning of this day, starting from the keynote by Professor Selly, and now Dr. Judy also shared with us. I'll be actually talking also about that, but and trying to, from a slightly different angle, so to say, and also trying to propose some mitigation means or some ways in which those problems can be mitigated. I won't be fixing the world, right? But I will just giving some pointers in the hopefully right directions. So this is my agenda, but let's skip it. I'll be definitely starting from motivations. And as I already said, I would like to say a few words about really the challenges of the data-centric AI. And my hypothesis is that the contemporary data science or contemporary machine learning is excessively data-centric. It's, in a sense, preoccupied with data. And we have many adages that actually refer to that, right? We say that the data is the new oil, or in God we trust, all others must bring data. And one of the drivers behind that, that position, that attitude, is that, unfortunately, as it happens with all the advantages of contemporary deep learning and machine learning, and the excellence in many different applications, the data efficiency of those approaches is extremely low, right? We need loads of data to make them work properly. And that's actually there's something wrong about that, right? Because humans can generalize really from very small samples of data. One of the very interesting researchers that I will point to at some point in my further point in my talk, Professor Joshua Tenenbaum of MIT, he actually brings that excellent example that for a kid, it's enough to see that just maybe a handful of examples of a cat, and that kid will actually grasp the idea and generalize almost perfectly and recognize cats everywhere. For contemporary deep learning models, that's actually impossible for many reasons, and actually the previous talk gave many reasons of that, the shortcuts being one of them. And I'm trying to also bring a few arguments to show that actually I would argue that data is of course essential, but learning from data without prior knowledge is actually impossible. And many of you may know that actually we have very strong theoretical reasons that actually results that actually prove that. And there's that famous North-Lange theorem, actually a series of theorems by Wolpert and his co-authors, who proves that actually if you have a classifier that doesn't have any biases, that classifier will not perform better than random. So actually all classifiers or all AI systems in general, I would put it, that do not have any biases, but of course, I mean the right biases. I mean the biases that actually direct the search in the hypothesis space in the right way, then actually without such prior knowledge, learning is actually impossible. So in a sense, the algorithm needs to know something about the problem and to actually be able to induce some valuable or useful hypothesis. Of course, those biases, those priors already exist in many of our approaches, right? Because, for instance, we assume that attributes have ordered scales, right? There are some other, of course, we make many statistical assumptions about data, and deep learning models also make such assumptions. But this is often not enough, right? And it's definitely worth remembering about that. And that makes it actually particularly difficult for deep learning models to cope with outliers, right? And that's another problem in a sense, actually very strongly related to the previous slide, but some of you may know this famous example of Waymo cars. Actually, it's a pretty old one, I think in 2016 or something like that, where a Waymo car was stunned actually and stopped entirely somewhere in the middle of the road in California. Why? Because actually it encountered in the middle of the road actually, and an elderly lady in a wheelchair chasing a duck with a broom, right? So it's extremely unusual combination, right? Fortunately, that particular AI system was equipped with all the kind of guardrails actually to behave properly in such a situation because it's unpredictable. But my argument is that the number of possible outliers is actually astronomical. There's no way to enumerate them. And that's a problem not only, of course, in autonomous driving, but actually in many other domains, including, unfortunately, healthcare. I hope that quite many of you are aware of the notion of combinatorial explosion, right? And the entities we deal with, including patients, are described or could be described by hypothetically by essentially an infinite number of attributes. And that's one problem already, right? And as it has been argued already in our talks here, many of those attributes are not even present in our records. But there's an even worse thing, right? That the possible number of combinations of those attributes is exponential. So a simple example, right? First you consider, you consider just a single attribute, right? A gender of a patient, then you consider you have the age of the patient, then you add the marker considering capturing arrhythmia, and so on and so forth. And with each additional attribute, your hypothesis space essentially increases multifold, right? It's not a linear extension. So in a sense, it increases a bit like a binary tree or an array tree. So, and that's a huge problem. And actually, this, if you think thoroughly, there's no way of addressing that with pure data, right? Meaning that for any reasonable practical problem, the number of attributes or aspects to be taken into account is too large, actually, to enumerate with pure data. So that will be my working or obsession, so to say, and theme. So, and of course, we know it actually, in a sense, also in many works considering that or proposing essentially the scientific process, so to say, by Popper and others, which argue, in my opinion, quite rightfully, that no amount of observational data or evidence can prove a theory to be true. We can only actually use that data to invalidate some hypothesis. Also, a very interesting argument I've heard many times from actually many interesting and excellent speakers and thinkers is that actually there's no such a thing like pure observation, right? You cannot make a pure observation without knowing actually what you are observing and what is the variable you are observing. So even in medical imaging, that I will be giving you a few examples. If you consider a value of a single pixel, right, then okay, you can state the fact that this value of this pixel is 184, but what does it mean, right? There's some essential interpretation behind that, right? There's some, for instance, some absorption coefficient, or there's some physical process that was actually at the root, was the root cause of that particular observation. And without this kind of insight, it's quite often difficult to make right decision, to make right inference, and it's very easy actually to fall victim to the kind of, for instance, spurious correlates and shortcuts that we just heard in this excellent previous talk. We always actually rely on some prior knowledge. And as a matter of fact, or fortunately, a bit of that prior knowledge is already included in our deep learning models. So for instance, as we know, and when we talk specifically about medical imaging and we rely on convolutional neural nets, and actually there are many priors in convolutional neural nets which concern, for instance, the fact that we are not like randomly permuting pixels. We are thinking about images as continuous spaces, right? And so that spatial organization of pixels does matter for us. The kind of operators we are using in those networks are also local, like pooling, right, or convolution. And we take into account some relationships between data and elements. For instance, the well-known attention mechanism in transformers and other architectures is a good example of that we care about relationships between some data entities, so to say. But actually, one can argue, and I would be still actually convinced to ask the question, is it enough? And in my opinion, it's definitely not enough. And the pilot approach I will be sharing with you in a few minutes is an example or demonstration of that. So in this slide, I'm starting to cover some other challenges for data-centric AI, or more specifically, for the kind of approaches which rely excessively on supervised learning. We know that, for instance, whenever you want to provide that supervision, providing that supervision or labeling is very costly, is very time-consuming, and very expensive, especially in the medical context, where you have to employ highly skilled professionals, which are expensive. Then we have the risk of biasing data annotation. I have a nice, I think, quite nice example from the ophthalmology, which I deal quite a lot on a day-to-day basis. For instance, we've been trying to, we've been trying to use the, we've been trying to train neural nets a long time ago, 10 years ago, actually the paper cited at the bottom of this slide, to detect blood vessels in fundus imaging, the basic imaging in ophthalmology. And at the top, you have the labeling provided by the physicians. At the bottom, the response of our best model. And that response, as a matter of fact, clinically speaking, is probably better than the labeling, because the model was eager, so to say, enough to suggest the presence of some very thin capillaries somewhere in the middle, not so far from fovea, while the experts labeling those images actually gave up, right? Meaning that either they were instructed not to touch that, actually, or maybe, simply speaking, they were not thorough enough to provide that labeling. So in statistically speaking, our model actually is now punished because it commits many false positive decisions. So that's another problem. The previous talk went through an excellent list of all sorts of spurious, variables and confounding variables and kind of ways or shortcuts that the models are extremely good at actually detecting. So I will probably skip this example, which is actually comes, I think, from the same work that Dr. Jury was quoting. Also, I would say there's also the kind of philosophical argument, meaning that in a sense, whenever we pose a machine learning task where the goal is to classify something, we require the models to be overly specialized. We in a sense, narrow the extremely wealthy, so to say, and rich complexity of this world to this very specific task where we have just a handful of classes, right? And we just ask the model to specialize on that. And that quite often leads to over-specialization, and the results are quite often poor. In a sense, I like to say, or to actually characterize this problem, that essentially we are, in my opinion, the contemporary AI is too much focused on predicting some dependent variables that we come up with, and not modeling actually the world. And if we try to model the world rather than to classify some phenomena, then we raise the bar actually for the models, because now they have to understand more about the world, right? And to somewhat, they are forced to come up with explanations of the entirety of what they observe, and not only some single dependent variable that we decided to pick for a given use case. And in that spirit now, I will try to point you to some possible avenues, actually, or means that may address those challenges. One of them is, and many of you probably know that, is unsupervised or self-supervised learning, or ideas or approaches in which we do not necessarily head towards classification, regression from the very start. But first we try to train some models which explain the data, and auto-associative learning, autoencoders, and similar models that can be trained in this way are actually very good, in my opinion, in that respect, because as I think most of you know, those models are required to, given some input, reproduce that input at the output, but the challenge is that they are forced to do that with a very narrow bottleneck of intermediate latent representation, which is very compact. For instance, in this particular study we did with my master's students a few years ago, the single piece of data that was presented to the model was a 11 by 11 by 11 voxel piece of OCT examination, and the model was forced to compress that to just 30 dimensional vector. So it's it's over 1,000 voxels here, and here we have that reduction to a very small dimensionality, which, by the way, and actually the model we were capable of training this kind of models almost to perfection, so to say, meaning that perfect reconstruction, which is quite impressive, but on the other hand also shows how much redundancy there is in image data, right? Because images are not just random mixtures of pixels, right? Our world is, so to say, lumpy, right? Most of the things that surround us are objects which are well defined, have some boundaries and so on, and this is the kind of data bias that the model can exploit. But most importantly, what we did in this particular work, after training this model, we worked quite hard on that latent representation, and we studied that latent representation in the search of clustering, or we use some kind of clustering algorithms to detect different types of cluster in that representation, to identify different types of voxels, and perform essentially unsupervised segmentation of those images. And what you see here is actually an example of such an unsupervised segmentation of an OCT slide around the fovea. Of course, clinically speaking, it's not particularly useful, right? It's far, far below the quality of what you can achieve with supervised learning. But this has been achieved actually with zero training data, with zero labeling. So I find it quite important. So that's one pointer, so to say. But I think more importantly, or I would say more interestingly, in more recent years, like for 4 years now, I'm trying to develop approaches in which, with my team, that essentially fall into the category of neurosymbolic systems. Many of you might have heard about them. It's an interesting trend, essentially within deep learning, on the verge between deep learning and good old-fashioned AI, in a sense, where we try to marry deep learning systems, deep learning architectures with symbolic reasoning. And there are actually quite many avenues towards that, because as a matter of fact, it turns out quite many symbolic inference models, or I would say symbolic knowledge representations, can be also expressed in a differentiable way. So there are many ways in which you can actually create a hybrid model which has a deep learning, or I would say typical deep learning component, combined with something which is symbolic. More specifically, in this quite, I would say, theoretical study, which doesn't refer to medical imaging at all, we constructed with my PhD student this kind of neurosymbolic autoencoder, where the encoder is essentially just a CNN, convolutional neural network, combined with a few layers, dense layers. But the decoder is essentially a differentiable renderer, which can be said to work in a specific DSL, domain-specific language, because it is forced to generate actually this kind of expressions, which are parameterized by the model. But these expressions, so to say, express or combine different image aspects, like rotation, scaling, the color of the object, and so on. And we've been training this kind of models on this kind of data, where, again, in an auto-associative manner, where the model was observing this kind of input and was producing this kind of output. And we were able to show that this kind of models actually, they learn very well, again, in an unsupervised way. Moreover, they actually were capable of learning shape prototypes, because the model itself actually is constructed in such a way that actually it identifies, actually, while learning, it actually identifies the prototypes of the shape. And quite importantly, and that's another argument of this kind, for this kind of approach, is that as it happens, because these neurosymbolic models are actually much more constrained than regular deep learning models, they also require fewer amounts of data. And we are able to show that this model performs very well, even if we reduce the amount of training data radically to just a fraction of the original volume. More recently, we've continued this kind of research already in the medical context, where with my actually bachelor students, and one of them is among that here, actually Kacper, we proposed an architecture which is actually very similar to the previous one, or even simpler in a sense. So we have, again, a kind of neurosymbolic autoencoder, which has a more or less regular, conventional convnet as the encoder, but on the output side, it actually performs, again, differential rendering with predefined shapes and very simple shapes, just ellipses. So actually, the model here is forced to respond to the input image by trying to reproduce that image with different ellipses, which have different, different squeezing factors, so to say, or that are differently elongated, rotated, and have different colors. And we used that model we trained it on pathomorphological data, more specifically on different types of anomalies of thyroid. And this is the input images presented to the model, and this is the response of the trained model. And of course, you may argue this response is really bad, right? Because, in terms of, if you measure the similarity in terms of mean square error or whatever of that output image to the input image, it's not particularly useful, right? It's any trivial, so to say, autoencoder or convolutional code autoencoder would perform better. But this is not the point here, right? The point here is actually to try to capture the structure of this histological material and actually the distribution of shapes and force the model to reason about the image not in terms of pixels, but actually some larger entities, like maybe something resembling cells or other anatomical structures. And even though it doesn't look good, then actually we were able to show that, diagnostically speaking, this actually performs pretty well. So this is actually, as a matter of fact, those samples came from three types of anomalies, so actually benign anomalies, anomaly Hashimoto, and nodularity. And what we did, after actually training this model in this particular unsupervised, again, way, without actually any access to labels, we then removed that decoder and we attached a classifier and actually, as you may see already, sorry for skipping this slide, the classifier to the output of that model, where that information flowing from the encoder to the classifier was also actually quite transparent, because those were the parameters of those ellipses. So actually, more specifically, statistics of those parameters, like what was the average slant, what was the average color, what was the average like proportions of the long axis and the short axis of the ellipse, and so on. So having this quite transparent set of attributes, we are able to train a transparent classifier, actually, as you may guess, a decision tree. And that decision tree achieved really good classification accuracy, or more specifically, you were able to show that this kind of approach and the final accuracy of classification was higher than what we could achieve if we trained on the same data a regular autoencoder. So we find it very promising. This thing is now under review, and we hope to get an acceptance, within weeks. So that's a very exciting thread of research for me at the moment. Yeah, of course, that's not the end in a sense, because I should probably emphasize that what I just showed is still very basic. You can see that in a sense, right? How can you describe the richness of histological tissue with just ellipses? Yeah, but that's what a pilot study, so to say. And one may ask, what is still missing from this kind of representation? And I would argue that definitely some kind of flexibility of representation, meaning that, in an image, including medical image, you can see quite often different number of components, the structures may be varying, the objects may be presented in different arrangements. And ideally, what one would like this to be modular and compositional, meaning maybe the model could, capture the idea that, let's say, a blood vessel is essentially a sequence of ellipses, right, for instance, or could be approximated by a sequence of ellipses or something like that. And one can ask, what is actually the kind of formalism that could capture this kind of flexibility and this kind of, provide this kind of flexibility and add it actually to this kind of neurosymbolic models? And my answer to that is that these are computer programs. And that brings me essentially to the idea of inviting program synthesis and the use of domain-specific languages within the realm of neurosymbolic models. And by programs, we mean here any essentially discrete, finite, executable structure that can be applied to any data. And you may know that actually we can have an amazing spectrum of possible program representations. But that's essentially a technical detail. More importantly, the whole idea here is that we are definitely in position now to build deep learning systems that, given some input, an image, but not necessarily an image, can respond to us in some kind of DSL. And of course, in a sense, LLMs do that to some extent. But in my research, I would like to do it in much more rigorous fashion, especially in a that self-supervised or non-supervised way via auto-association. And as a matter of fact, there are many ways in which this can be approached, and I'm quite happy that given that I do have some background here, because actually I've been studying program synthesis for some time and actually working on different ways of synthesizing programs from examples. You can do it in different ways, using principled approaches, or using even evolutionary computation and other, and more contemporary deep learning as well, of course. I will skip probably this slide because it's probably quite dense. I would like also to point you to the fact that actually there are very strong parallels actually between machine learning and program synthesis, because in a sense our machine learning models are programs, are essential instances of very simple programs. Those programs typically don't have loops, don't have branching instructions, but they are in a sense statements that do something, right? Then knowledge representation can be likened to a grammar. The process of fitting a model to the data is a bit like program synthesis, right? And we also even have the so-called representation biases, which we know in machine learning, which in the case of program synthesis can be given by picking or designing a specific domain-specific language. Okay. Fortunately, and I would like to point you to the fact that this is indeed already happening to some extent, and we have excellent works from all over the world, including this one from the team by Joshua Denenbaum that I mentioned earlier, where deep learning models are being built that marry, so to say, the purely, let's say, dense, I would say deep learning or conventional deep learning inference and some elements of reinforcement learning with program synthesis, where in this particular work, this model was solving the so-called visual query answering problem by actually translating the queries given in natural language into statements in the specific domain-specific language, and then actually executing those queries, or executing those programs. This was actually before the LLM era, but I still find that this is actually quite promising. In my lab, we are working on different problems using similar approaches. Just briefly, you may have heard about this famous ARC challenge, abstract reasoning challenge, a famous benchmark in fundamental AI, where the challenge is posed to the learner, if they're human or a system, is to, given a very small number, a handful of input-output mappings, infer a rule that actually maps inputs to outputs and prove that that inference is correct by applying that rule to a new example and showing that that the system actually captured the pattern. This is a super difficult benchmark posed by Francois Chollet, that the co-author of Keras, or actually main author of Keras, which is still actually quite difficult to solve even using LLMs. So we have some interesting preliminary results with that. I will now wrap up. I hope this somehow was maybe to some extent novel to you, and I would definitely argue that we are at a very interesting point of development. The take-home message from me to you would be that please don't think that data is everything. Prior knowledge is essential for efficient learning. I claim that contemporary AI is too data-centric, but of course we need data, but that data needs to come to us together with some prior knowledge. And there are vast repositories of medical knowledge available, like ontologies, right, on standards and so on. And I find neurosymbolic systems quite an interesting avenue towards this kind of architectures. And what this can bring us are all sorts of benefits, like better data efficiency, lower demands on annotation, as I said, modularity, compositionality, and other advantages. So with that, I would like to conclude that, of course, you can claim that data indeed is the new oil, but extraction of oil requires knowledge. Thank you very much.